if we have a charged particle and it's in electric and magnetic fields, it feels forces given by the electric force. This is an external electric field. And if the charged particle is moving, there's a magnetic force given by, together, the Lorentz force law. Let's consider a case where a charge is moving with a velocity v in this direction, and it enters a region of an electric field pointing directly down. And let's make this charged particle positive. And in this same region, there is a magnetic field directed into the plane of the figure. We'll call that B. So let's choose some unit vectors, I hat, j hat, and k hat. Now, let's ask ourselves, what is the relationship between the electric and magnetic fields such that the charged particle will undergo straight line linear motion? And that's the case when the acceleration is 0. And so what we have over here is QE plus Q VQ cross B. Now, in our coordinate system, because if we want to write all of this out, the electric field, a constant, it's uniform, it points down. The magnetic field is pointing minus B k hat, and the charged particle is moving with speed v in the I hat direction. And so we can put these in E j hat plus Q v I hat cross minus B k hat. And we want this to be equal to 0. And what we see is we have QE j hat. I hat cross k hat is minus j hat, but another sign gives us a positive j hat. And so our condition that the particle will undergo straight motion is just that QE is equal to QVB. And so we see that if the velocity is equal to E, the speed is equal to E over B, that's the relationship between these fields, then this particle will go directly through and experience no net force.
OK, suppose somebody asks you, or you ask me, what are the units of magnetic field? How do I figure the answer out? Well, anytime anybody asks you what the units are of anything, the way that you figure the answer out is you ask yourself, can I think of an equation in which magnetic field occurs where everything else in the equation I already know what the units are? What's an equation with magnetic field in it? Well, what about the force law that we just learned? If I have a charge Q and it's in a magnetic field B, what's the force on it? Well, it's QV cross B. So here's an equation in which magnetic field occurs. This says that if I have a charge in a magnetic field, if the charge is at rest, it doesn't feel any force. But if it's moving with a velocity v, it feels a force v cross b times the charge q. And I do, in fact, know the units of everything else in this equation. Force is in newtons, q is in coulombs, and v is in meters per second. And so that tells me that the units of B are what? Well, that tells me that the units of B must be the units of force, which is the Newton, divided by the units of charge, which is the Coulomb, divided by the units of velocity, which is the meter per second. So there's my answer. The units of magnetic field are newtons per Coulomb meter, and then the seconds was there. Newtons times seconds per Coulomb times meters. So we're going to give a name to this in a second, but before I give a name to it, notice that a Coulomb per second, that's an ampere. So this is also the newtons, the units of magnetic field are newtons per ampere meter. But I don't want to keep going around and saying the magnetic field is 27 newtons per ampere meter. I want to name this unit, and the conventional name for this unit is named after another pioneer of electricity and magnetism. This is called the Tesla, named after Nikola Tesla, who now has a car company named after him also. So the units of magnetic field are a Tesla, Newton per ampere meter, conventionally called capital T or Tesla. How big is a Tesla? Well, let's walk our way through the size of various different magnetic fields that you might be familiar with or interested to learn about. So first of all, what about the magnetic field of the Earth? How big is that? Well, the magnetic field of the Earth is about 5 times 10 to the minus 5 Tesla, which is conventionally called 0.5 Gauss. So what is a Gauss? Well, a Gauss is an equivalent unit of magnetic field. We could do everything in Gauss or everything in Tesla, because what is a Gauss? Well, a Gauss is simply 10 to the minus 4 Tesla. So the magnetic field that we are familiar with, because we are immersed in it all the time, is about half a Gauss, or 5 times 10 to the minus 5 Tesla. What does that mean? Well, that means that, remembering the equation that we used to work out the units in the first place, QV cross B, what that means is that if I'm carrying around an entire coulomb of charge, and I'm moving it at 1 meter per second through the Earth's magnetic field, then the force on it is going to be about 5 times 10 to the minus 5 newtons, which is a very small force, and a coulomb of charge is a lot of charge. So the Earth's magnetic field is really quite weak. When I walk around in it, I don't feel the fact that the charges in my body are moving through the Earth's magnetic field doesn't have any discernible effect on me. It is true that if you have a compass needle, you can detect that magnetic field. We know it's there, but by most measures, its effects are small. So what other magnetic fields might you be interested in knowing the size of? Well, all of us have electric currents in our brain, and those currents make magnetic fields. And if you ask, how big is the magnetic fields right at my scalp because of the electric currents flowing in the nerve cells in my brain, those magnetic fields are even smaller. A femtotesla. What's another familiar magnetic field? Well, what about our refrigerator magnet? Refrigerator magnets make a magnetic field which is bigger than that of the Earth. It's typically around 10 to the minus 3 Tesla, or 10 Gauss. A little bit bigger, but still a few Gauss. Not that much bigger than the magnetic field of the Earth. One place where I hope you don't have experience with it, but which you might one day, where the magnetic fields are much bigger, is an MRI magnet. So if you need to go to the hospital to get an MRI done on your knee or on some other part of your body, you stick your knee or whatever part of the body is being imaged with magnetic resonance imaging, you stick your knee into an MRI magnet, and the magnetic field in a typical MRI magnet is about 3 Tesla. So that is about 60,000 times stronger than the magnetic field of the Earth, about 3,000 times stronger than the magnetic field of a refrigerator magnet. So in thinking about the unit, the Tesla, Tesla's not quite an everyday unit, because the everyday magnetic fields that, like the Earth's magnetic field or refrigerator magnet, are smaller than a Tesla. They're about a millitesla for the refrigerator magnet, or 5 times 10 to the minus 5 Tesla for the Earth's magnetic field. But a Tesla is an easily achievable field by standard human-built technology. Every hospital in the United States has a 3 Tesla field in the MRI magnet down in the basement. Can you get larger than that? Yes, you can. In many physics labs, you will find magnets. So in a physics lab, for example, in the building in which I am right now, there's an NMR magnet which achieves fields of about 18 Tesla. The largest magnetic fields that are produced in laboratories can be bigger than this also. The largest fields, though, are not produced in a steady fashion. You can get fields of around 150 Tesla, but they're pulsed. This 18 Tesla magnet, which is in the basement of the same building that I'm in right now, when it's on, it generates an 18 Tesla field that's continuous. It's always there when it's on. The 150 Tesla magnets that you'll find in some other labs can only produce this strong of a magnetic field for a brief moment in time. They're pulsed. So you can easily get up to tens of Tesla with human-built technology, but nature is much, much better at making magnetic fields than that. The largest magnetic fields in nature are enormous. The strongest magnetic fields in nature, as far as we know, are the magnetic fields of certain pulsars. A pulsar is a spinning neutron star. What's a neutron star? A neutron star, it's the cold ember of a supernova explosion in which a giant star, at the end of its fuel-burning life, explodes, makes a violent display, which people can see with telescopes from across in distant galaxies. Even they're incredibly bright. And then after the supernova goes off, the remnant that's left behind is a neutron star, which might have a mass comparable to that of the sun, but is only about 10 kilometers in diameter. So they are incredibly dense. They're spinning incredibly fast, and they have incredibly large magnetic fields. They can easily have magnetic fields of 10 to the 8th Tesla. And in fact, these are surface fields. The interior fields are probably larger still. So this is the record as far as magnetic fields on large scales in nature. In a sense, the record for human-built magnetic fields is actually not this. In a sense, it's the Large Hadron Collider. In the very first video segment of 802, I told you about the Large Hadron Collider, and I mentioned that the Large Hadron Collider is an extraordinary piece of technology, and that technology is entirely built on Maxwell's equations. And that piece of technology built on Maxwell's equations was used to test Higgs's equations. But one of the ways to see what I mean by this technology being built on Maxwell's equations is to realize that that accelerator, the Large Hadron Collider, is made of magnets whose magnetic field is 8.4 Tesla, at which point you say, well, that's not a record, 8.4 Tesla. You said that in the basement of the building that you were standing in, there's 18 Tesla. But yes, the 18 Tesla in the basement of this building is over a volume about this big. This 8.4 Tesla at the LHC is over a volume that's 27 kilometers long. So over filling a ring, which is 27 kilometers long and about this diameter, a tube about this diameter, 27 kilometers around, you have an 8.4 Tesla magnetic field. This means that the LHC magnets are by far, by orders of magnitude, the human-made magnets with the most magnetic field energy in them. And just as we've seen that electric fields have energy, we're going to see that magnetic fields have energy. We'll see that a little ways on. And but the magnetic field energy in the LHC magnets is dwarfed by that in a neutron star. So nature still wins.
All right, so next we want to look at an example of a charged particle moving through a uniform magnetic field. So here we have a charged particle, a charged positive particle, and it's moving with some constant velocity v. Now the magnetic field in this example is going to be uniform, and everywhere it's going to be going into the board. So this is my magnetic field B. Now in this problem we can define a coordinate system, and I'm going to use the coordinate system where I hat is there, J hat points up, and in this case K hat would be coming out of the board, which means that our magnetic field B is equal to the magnitude of the magnetic field, and it's in the minus K hat direction. So now if we want to look at the motion that this charged particle is going to undertake, we first need to look at the force on that particle. So the force of this particle we know is just equal to the charge times the velocity cross the magnetic field. So in this case, we have a charge. Our velocity is in the j hat direction, and we take the cross product with our magnetic field, which is B, in the minus k hat direction. Now you can use your right-hand rule, or you can take the vector cross product there, and you'll get that this gives you q, v, b, and the direction is going to be in the minus I hat direction. So if I come back over to my figure, I see that my force is pushing me in the minus I hat direction. So what we have here is a force that is everywhere perpendicular to the velocity, and it's pointed off in the minus I hat direction. And so we know what that's going to look like. That is, it's going to look like a circular trajectory. Okay, so since we know this is going to be circular motion, we can next ask what the radius of this trajectory is going to be. And to solve for that, we use the fact that our force for circular motion is equal to the mass of the particle times the velocity squared divided by the radius. And we know that that force is equivalent to Q times V times B. So we can put that together and solve for R. That gives us a radius of our motion that's equal to mv divided by qb. The next thing we can ask then is what the period of this motion is. So we can ask what is the period of time t that it takes for this charge to move around its circle and come back to where it started. Well, that's just equal to 2 pi times the radius of the motion divided by the velocity, or if we plug back in our expression for the radius, we get that that's 2 pi times the mass divided by qb. The last thing we want to know is the angular velocity of this particle. So that's our omega. Omega is defined as 2 pi divided by the period t. And again, we can use our expression for the period, and we see that that's equal to qb divided by m.